Okay. Okay, so we are here to discuss about this fracture. So as the definition is there, it is basically the separation of the basically one body. There is a body. It is basically a separation of one body into two parts or maybe more than two parts. Like suppose once the fracture happens, then it may be the most chances is that it will break into two parts, but sometimes it can also break in more than two parts also. And for this fracture, basically the root cause which is there is a presence of some kind of cracks, and this crack can be initially when the material is being manufactured, or it can develop with the help of application of some stresses. Okay, and there are some defects which can also lead to the development of the crack. So we will discuss that. But whenever we say a fracture, then fracture is of two types. So one is ductile fracture, another is brittle fracture. Okay, these are two types. These are basically two extremes of fracture, I want to say. Like this is the top one, that is the brittle one, that material will fail suddenly. Okay, and the most bottom one is the ductile one, that will uh, fail, but that will fail progressively. That means you will have ample time to check, okay, this part it is elongating or getting thinning, something like that, and you will be able to recognize it, and you may correct it also, or save it basically from different failure. Okay. Okay, so basically once the failure happens, so it is generally a mix of brittle and ductile, but you will see that most of the component, most of the things, like suppose I am studying a ductile fracture, then it can't be like it is 100% ductile. Okay, these are two extremes. Maybe 0.1%, 1% it is brittle. Somewhere you will see that some brittle characteristics is also there. Okay, so let's proceed. So these are some of the features. So this is very ductile. So as I have told you also during the tensile test, what happens, the thinning of the specimen, the more thinning it will take, that means the more ductile it will be. So if specimen thins like this in a pointed way, that means it is holding some force up to the thinning of this much of lesser diameter. So that means it is able to hold, to resist the failure for a longer time. This is somewhat moderate ductile. That means the thinning is there, but it's not like it's very thin, but somewhat significant thinning is there. Okay, and this is the specimen where we do not observe any thinning, but it fails. Okay, and the surface feature is also something like flat, here it is given. So this is the very much exaggerated form of brittle fracture. Actually not all brittle fracture is very flat, but you will come to know that surface it looks like it is a very planar. Okay, so that's why here it is marked like this. Okay, so you can see the two figures which are very beautifully explaining what is the ductile fracture and the brittle fracture. So this is the ductile fracture, this is the diameter, and this is the thinning over here, right? Here you can see this is the initial one where it has not thin, it is basically uniform, and here it is thinning, and these are two part of the same specimen. Okay, and you can see here it is making some kind of uh, basically it is the phenomenon, if you see in the case of ductile, that is with the help of voids, so that creates some kind of, you will see, like pits, okay, like that. Okay, now you see this fracture, this is the brittle fracture. So this is very beautiful fracture. You can see there is no any thinning and the surface is very flat. Okay, so one is ductile, another is brittle, and this thinning happens because of this plastic deformation. Okay, it is basically because of plastic deformation, and here no plastic deformation happens. Okay, these are some other examples of ductile failure. So this is for the pipe, so it has failed at one location, and this is the brittle failure where the pipe has been disintegrated into various parts. Okay, okay, so now we will study one by one. So basically the ductile failure. So in the case of ductile failure, basically there is a specimen, we are applying the force. So what happens, the thinning will happen, and the thinning, it is called as necking. So if you remember this stress strain diagram, it was something like this, right? So this is the point up to which it will be elastic, that means it is straight line, then it will curve, and it starts curving with a higher stress. Then after this, somewhere at higher stress, we decrease it. Okay, it starts decreasing. So this highest point, whatever it is, that is called as the UTS, and here the necking phenomena happens, because after this material is not able to bear load because the thinning will happen. So that's what it is showing you, the thinning. Okay, so and while the thinning it happens, so it is said that inside of that material, so there are voids means open spaces, like I told you about the vacancy. So like the vacancy, there are some voids. So when many vacancies accumulate at one place, then that is called as void. Okay, so these are small voids which will be there, and by the application of this stress, so what happens, these voids will grow. Okay, these voids will grow, and once this void will grow, then these voids will also come together, because there is a permanent application of force over there at that point of time. So that voids basically mix with each other, that is called as coalescence. Okay, and this is the area which is open and it is not basically taking your force. So what happens, just after that the crack it is formed, and it leads to it propagates, and basically it leads to the failure. Okay, so that's why when we see a ductile fracture, then we will see like a cup and cone. Basically it is called as cup and cone, cup and cone, right? Cup looks like this. Okay, like we have a space where we put the tea. So cup, and the cone, it is it is angular, pointed, so something like it is fitting over there, cup and cone, right? So that's what we can see here. I will just show you the ductile one. See, this is also cup and cone. So this surface is like a cup and this is like a cone. Okay, and this is the broad picture, and if you see at the microscope level, so also, so there you will see like that. Okay, so these are some of the micrograph it is shown. Okay, So you see this feature, if you see, this is your able to see, like it is something like a pit, round pit. Okay, so this is cup. Okay, and if you see the other part, because if in one sample it is cup, then in the other broken part it must be the cone. Okay, because then only it will fit, right? So if you see the same reason here for this, so here you can see these are some spikes like things are there, right? So these are cones and these are cups, and here it is also showing that, like, these are some particles. Okay, these are some particles, some extra particles that can also lead to the formation of voids over there, because these are some secondary particle. Here the bonding between this particle and this metal will be somewhat different, so when the application of force it happens, then there will be chances that it can form a void. Okay, so it happens like that. So this is for ductile fracture. And for this brittle fracture, okay, so this brittle fracture, basically what happens, uh, here the concept is somewhat different. It is like there is some crack, which we understand that there is some crack. That crack basically propagate instantaneously with the application of stress. Okay, so when it propagates, then it creates a very flat surface, and this propagation can be along the grain and between the grain also. Okay, so once it happens along the grain, then this is called intergranular, and when it happens across the grain, then that is called a transgranular. Okay, so this is some feature it is shown. So this is also showing you, like, this is some kind of V shape. I had also told you that the surface, it it is flat, but it's not like it is truly very flat. You can see there are some ups and downs over here, but you can say the overall there is no cup and cone here. There is a feature, you can see this is V shape chevron marking. Marking means, you can see here, like this looks like something like this. These are something like this. So these points which are there, so basically that denotes the location of the crack. Okay, so this is the first point where the crack initially it is there. So when we are applying the force, so from here you see this region is flat, so it is trying to propagate. Okay, once it is trying to propagate, and this will lead to complete specimen, it will travel, and basically it will fail. Okay, yeah, some more pictures of brittle fracture. So basically you can see this is the specimen and these are the grains, right? These are the grains, and these grains, you see this is the grain boundary where the fracture it is happening, right? So this is called as intergranular. Okay, between the grain. And you can see the next picture. So you can see the next picture, these are the grains and this is the crack, so it is traveling between the grains. Okay, so between the grains also the fracture can propagate. Okay, so what does this crack do when we apply the stress? Okay, so if the crack is there, so the crack region which is there, so the stress which we apply, that is homogeneously applied along the specimen. But suppose there is some point where we have some extra atom, we have some crack, So at that point the stress will rise. At that particular point only the stresses will rise. Why stress will rise? Because the force which you are applying, so that is somewhat same, but force divided by the area. So area of a crack decreases, area of a secondary particle it will decrease, because these are discontinuous thing. So that will itself act as a single body, like that. So there the force which is there same, so the stress will increase. So once the stress will increase, so that will be beyond its elastic and plastic, basically that will lead to formation of crack. Okay, so that's what here it is explained. This is the fracture mechanism. Okay, so here this is the specimen in the form of 2D, two dimension. Okay, and from inside it is shown that there is some crack, and this crack has a length of, this complete length of 2a. Okay, and this is the formula where we are able to see the stress amplification, like how much it is amplifying. So basically this sigma m is equal to 2 sigma naught a by rho t. Rho t is curvature of this crack. Okay, so rho t is nothing but b square by a. So b square, how it will be, because this is, we are assuming like a ellipse. So this is your major axis, this is your 2a. So this minor axis, this is your 2b. Okay, so you can see at this point or this point the stress is very high. This is 2 times of sigma naught. Sigma naught is the application which we are applying, sigma naught, and a divided by rho t, because this rho t is b square by a, so that will be very low, and this is a, so this will be high. So like that it is higher. Okay, so that's what it is shown, that at this point you can see the stress which is there. So this is sigma m, which comes from this formula. Okay, and here also this is, and this increase from this, if you calculate, then this is called as stress concentration factor, the factor through which the stress is increasing. So that is called as stress concentration factor. Means at that particular point what is the concentrated stress which has increased. Okay, so this is the ratio of that. Okay, so this is my first video. I will also record and send you the next video. Okay, thanks.